Perhaps you have already seen mining farms that create Bitcoin, but did you wonder how the miner itself is constructed? What's inside and how does it work? Let's look at the example of the most popular miner, Antminer S9, manufactured by Bitmain. This miner is an aluminium base in the form of a thin wallet tube of square section. On the ends of the pipe there are two fans, whose task is to provide a quality air cooling to the miner. Inside the base there are three cards with ASIC chips. Each of them is covered with aluminum radiators for better dissipation of generated heat. Now let's look at the way the chip works. The microscope is a plastic base with metal pins on each side. They serve to establish a contact with the conductors on the electronic board, to which the chip will subsequently be installed. Inside the plastic base there is a crystal chip to which thin metal hairs leading to the pins are soldered. You can see the crystal itself through the glass window, which is set for clarity. The crystals are made in the form of one large round plate. Each such plate can contain several hundreds or even thousands of crystals. After the plate is cut into separate pieces, each of these crystals will find its place in a separate chip. Well, now you know how a chip differs from a crystal. Now let's immerse in the device of the crystal and try to see the transistor there. To begin with, we need to cut out the crystal from the common plate. Now if we enlarge it, we will see the following picture. On the crystal you will see a lot of small similar blocks resembling crystals, which we saw in a silicon slab. Inside these blocks we will see some individual structural elements. For example, narrow strips of the lines of input-output information, and cells with squares are computing cores. The core is a minimally necessary functional block of the integrated circuit, which is capable of performing the required computational task. From a technical point of view, in order to make our chip work, only one core is enough, but if we wanted to do as much work as possible, we need to place a lot of cores on its square. Cores are just those workers who perform the basic work, computing hashes of bitcoins. Each separate core computes 1 hash for a unit of time. 10 cores per time compute 10 hashes, 100 cores, 100. The more cores on the chip, the more hashes for the same time compute one chip. Let's look inside the core. We use a powerful optical microscope for this purpose. When considering a structure, we will see a grid consisting of very small cells, which are aligned strictly horizontally and vertically. These cells are just densely packed field effect transistors. As you can see, even with very strong magnification of the optical microscope, we cannot see a single transistor to observe its structure. For this purpose, we will have to use an electron microscope. Under the electron microscope, we are able to observe what exactly creates the effect of the grid structure. These are wires that are soldered to the surface of individual semiconductor blocks of which individual transistor consists. These wires go over the entire surface of the core, connecting the transistors to each other, as well as to the inputs and outputs through which the core receives data, and the result of the calculations is returned. With a strong magnification, we can see a single transistor in close-up. Each such box to which 3 wires are soldered is our transistor. Larger rectangles are gates that consist of several transistors. As you can see, they all have different configurations because different types of transistors are used, so that you can assemble different types of gates from them. Well, let's look at the way it's done. The simplest gate is an inverter. It has only one entrance and one exit. Its logical function is that it converts a high voltage into a low voltage, and a low one vice versa into a high one. For its implementation, 2 field effect transistors are needed. More complex gates, having 2 or more inputs, require much more transistors to implement their logical function. For example, the gate NAND is assembled from 4 field effect transistors and the OR element of 6. For a better understanding, compare what the NAND gate looks like on the schematic diagram and in the form of schematic representation of the physical layers of materials from which it consists. As on a larger scheme, it's very difficult to understand which transistors belong to a particular gate. They are usually combining blocks that have symbolic designations of a given gate. A circuit designer deals with these units, and he develops architectures of digital devices. So we got to the following definition: architecture. The architecture of a digital device is a selected set of gates, their location relatively to each other, and the electrical connections established between them, which are designed to process incoming signals according to a given algorithm. Two different circuit designers can create completely different architectures that solve the same task. We will analyze this with the example of the gate XOR. This gate has 2 inputs and 1 output. It doesn't respond to low voltage signals on both inputs, but only works if one of the inputs has a high voltage. At the same time, a feature of its work is that in case that high voltage levels are applied to both inputs, this element should not be triggered. Let's try to assemble it. Here is the first version of its assembly. It consists of 4 elements, AND, 3 OR, and 1 NAND. The total number of transistors needed to implement this scheme is 46. Let's check whether this circuit works. It reacts to the high level of the signal on the upper wire. To the high level of the signal on the bottom wire, it also reacts, but on high levels of both wires it doesn't. As you can see, the circuit works. However, this scheme requires a lot of transistors. Let's try to assemble a more compact scheme, for example this one. Now our scheme consists of only 3 gates, 1 NAND, 1 AND, and 1 OR. This reduces the total number of transistors in the circuit to 16, and this is almost 3 times less than in the previous one. Well, and the most compact variant is a logic circuit XOR, which is assembled from 8 transistors only. As you can see, one and the same computing task can be solved in different ways, using different sets of gates and connections between them. This is what is called architecture. At the moment, we are looking at 3 different architectures of XOR. All of them use a different number of transistors, which means they will occupy different areas on the crystal. I hope now you have a clear picture of how a chip of the miner is structured, how a core differs from a crystal, and what the term architecture means. The video was created as a part of the Venus Mine project. Thank you for your attention. All the best to you.